Welcome back. We're next going to be looking at question number 14 to continue our work through this video solutions for the related rates basics problem set. And in this one, we're going to begin with question number 14, picking up right where we left off yesterday in the middle of the Pythagorean examples that we can see. So in question number 14, we're told at the very beginning that while training in hopes of becoming a member of the Avengers, actually it just says Avenger, that's amusing, Spider-Man begins climbing a vertical wall at a rate of 7 feet per second, watching from 180 feet away horizontally. Tony Stark looks on with keen interest. So first, let's try to draw this situation a little bit, just to get an idea of what this picture actually looks like. I know I mentioned that it was Pythagorean, but there's no proof of that just yet, so let's do it carefully. So first of all, there's our wall that we're looking at. And for our Spider-Man, let's take advantage of the Google. Actually, that might be a little bit too small. And remember, of course, all things are registered trademarks of Marvel and Disney and all that good stuff. So there is our Spider-Man climbing a wall. Let's put it right there. Oh, it looks like he's sort of climbing, although his mask should probably be on, otherwise people will be able to know who he is, and Marvel would never let that happen. What else does it say? It says, watching from 180 horizontal feet away, Tony Stark looks on with keen interest. Tony Stark, there's a character that can stand the test of time. So let's see. So here is Mr. Stark. He's watching somewhere over here. And I'm thinking this is one of those problems where we're going to have to assume that we don't care how tall the person is. We're just going negligible with eye distance, or with eye height. So there's Tony. There's Spider-Man. Everything's set up in our picture. So now it says that he's 180 horizontal feet away. Boom. And then, of course, with those two pieces in place, the distance between the two of them is going to form the hypotenuse of a particular right triangle. So right there already we can kind of see what's going on in our situation. We've got a right triangle situation, so we're thinking Pythagorean identities should be helpful. Or Pythagorean, not identities, just the Pythagorean theorem itself should be useful. So what else do we know? Spider-Man's climbing the wall. Let's call that vertical wall, let's call it Y. And he's climbing up the wall at a rate of 7 feet per second. So 7 feet per second. And then watching from 180 horizontal feet away. So Stark's not moving at all right now. So I'm just going to put 180 feet outside. And of course that leaves us with a hypotenuse, which I'm going to call D. And then we'll have to figure out what it actually is. So everything's set there. The only thing moving right now is Spider-Man going up, and as Spider-Man goes upward, the diagonal distance, or the length of the hypotenuse, is increasing too. So from here, our two questions. I've put two on the first page, simply because they're very related. It says first, at the instant when Spider-Man is 112 feet above the ground. So to prepare for this, let me get a different color. So Spider-Man is 112 feet above the ground. What is the diagonal distance between Stark and Spider-Man? So we're trying to figure out what the diagonal distance is, and we already said that that diagonal distance was going to be D. So we're going to be looking for D in our picture. We're going to try to solve for that. And what we're told here that we didn't know before is that Spider-Man is 112 feet above the ground. So we know the snapshot moment or the measurement. So for this first problem, there's not actually any calculus to do here. We want to figure out what the diagonal distance is between them. Well, we have 180 for one length. We have 112 for the other. So we can just use the straight up Pythagorean theorem. We'll have 180 squared plus 112 squared equals that distance D squared. And again, using our calculator, I should probably pull that out. There it is. So pulling up our graphing calculator, just so we have a calculator handy. You'll quickly realize that I typically do make these Pythagorean triples so that all three are positive integers, but theoretically it might not be that way always. So in this case we want 180 squared plus 112 squared, and then we want to take the square root of the answer. We get 212. Cool. So that tells us that the diagonal distance we're looking for is 212 feet. So there's the answer to our first question, and just as relevant, we can place that onto our triangle. So we now know the snapshot length. If we're interested in the times and rates at which things are changing when Spider-Man is 112 feet above the ground, we know what the hypotenuse would be at that instant. So part A is finished. part B, though, we're going to have to do a little bit of work with. So for part B, it says that the instant when Spider-Man is 112 feet above the ground, at what rate is the diagonal distance between Stark and Spider-Man changing? So now we want to talk about the diagonal distance and its rate of change. So we're looking for dd dt, which we might otherwise call capital D prime. So in order to get there, we need to relate everything in part B so that we can eventually take the derivative. Oh, don't know why I have an equal sign. So in here, I'm going to start with the Pythagorean relationship. We're talking about how fast one of the lengths of the sides of the triangle is changing. So we need to find some relationship that involves the lengths. And since we already know two lengths, as well as how fast one is changing, we might as well start with the Pythagorean theorem. So in here, I've got to be careful, though. When I write my equation, we have y squared plus 180 squared. And if you're curious why I'm putting in 180, it's because, again, this isn't changing. This length is constant because Tony Stark's just standing there. I don't know, probably on his smartphone or something. Or trying to figure out some way to time travel or something like that. Just standing in place, a set horizontal distance from the base of the building where Peter, Spider-Man, is climbing. So that one's not changing. Whereas on the other hand, the hypotenuse is, of course, changing. So we need to include that as a variable. So that way the changing things are represented by variables. From here, our next move now is to take the derivative with respect to t of each of these. Because, of course, that will allow us to relate the rates together, the rate at which Peter's going up and the rate at which the hypotenuse itself is changing. So in looking here, again, knowing that we're differentiating with respect to t, and there are no t's in that equation, we can go ahead and rewrite this equation, or we can differentiate the equation and get 2y times dy dt plus 0, because 180 squared is just a number, so it's constant, and its rate of change or derivative is 0. And on the other side, we'll get 2 capital D times d prime. And if we divide both sides by 2, we'll get that y times y prime is equal to d times d prime. So good stuff so far. What's next here? So what do we got? We got the instant when Spider-Man is 112. Oh, let's look at all these pieces. So y itself is now we're ready to snapshot because we already took the derivative. Our differentiation is complete. We're going to let y equal 112. Y prime is the rate at which Spider-Man's going up, and we also have that. They told us it was 7 feet per second, and it's going to stay positive because of the fact that he's ascending. So his height on the building is getting bigger as time goes forward. For the hypotenuse, we know at this instant d is 212. We don't know what d prime is, but that's okay, because we were trying to figure out the rate at which the hypotenuse was changing. So moving some stuff over here, we're going to get really quickly that d prime, otherwise known as dd dt, is going to be equal to 112 times 7 over 212. That's the same thing as, I believe, 784 over 212. And I mean, at this point, I could just keep simplifying as best as I could, but I happen to know that that simplifies to 196 over 53. As far as units, we've got feet per second. You can tell that based on everything that's measured up there. And I will point out that oftentimes on these, a rounded answer, or an approximate answer is great, as long as it's accurate to the appropriate number of decimal places. And if we do 196 over 53, 196 divided by 53, we are in fact going to get 3.698. So that distance between them, which maybe would be relevant to a superhuman with the ability to shoot spiderweb sort of stuff out of his wrist launcher and cover a short distance in a short time. We know that the distance between them is basically increasing by a little bit, around 3 3/5 feet per second. Okay, now that brings us to question 14c, which is, I think, the real interesting question here. In 14c, it starts by telling us that we're at the same exact snapshot moment. It's at the instant when Spider-Man is 112 feet above the ground. At what rate is the angle of elevation from Stark to Spider-Man changing? So our picture is getting an addition. There's a new addition in here. And to help me with that, I'm going to go ahead and copy my picture over, because everything else about this picture remains just as accurate as it was. So first of all, there's our picture. I'll just uncircle a couple different things. What we're being asked about this time is not the side lengths themselves. We're being asked specifically about the angle theta there, the angle of elevation from, it looks like, Stark's toes up to where Peter/Spider-Man is on the wall. So if that's true, we're going to need to relate some information together that involves not just side lengths, but also the angle theta. And that suggests to me that we're going to want to use some trigonometry. We'll want to use one of the trig ratios to relate these pieces together, because trig ratios absolutely relate angle to side lengths. So in here, the question might be, which one do we choose? So there's a bunch of different ways to go here. The first thing I'm going to demonstrate, though, or explain to you, is that there is one that's typically the easiest possible way to go through. What you're looking for in the easiest possible one is you're looking for a trig ratio where, one, you can differentiate it, because obviously if secant's the easiest and you don't know what the derivative of secant is, so you can't remember it, then that's not a good thing. But two, you're looking for one that has a variable over a constant value as the ratio. In other words, where one portion is changing and the other one is not, simply because that will eliminate the need for the quotient rule. It doesn't matter which ratio you choose, though, so if you're not sure, you're having trouble deciding at any point, just pick whichever one feels easiest to you and just differentiate it faithfully using the implicit differentiation tools. So from here, first I wanted to do the ideal match, and in looking, I'm looking for one that has something over a constant value. So what I see is that if I choose opposite over adjacent, then I'm going to get y over 180, because the 180, or that distance from the base of the building to Tony Stark, that distance isn't changing. It's almost like Tony Stark isn't moving. Like, he can't move. Oh well, get it out of my head. So from here, what we're going to start with is we're going to start with exactly that ratio. So I'm going to start with tangent of theta. Looking at our picture and including things that are changing, because for instance, theta is clearly changing right now, so we keep it as a variable. Opposite is y. The height of Spider-Man is changing as he climbs further and further up. And over adjacent, which is 180, which is not changing, because Tony Stark is not moving. So from here, we've got to now work our way through. In fact, we're ready to do the normal implicit differentiation techniques. We're going to differentiate this thing with respect to time. So looking over there, we first have tangent of theta. Well, the derivative of tangent is secant squared. So we're going to have secant squared of theta, but since theta is changing, because obviously as Peter gets higher up the wall, that angle increases, and if Peter goes down the wall, that angle decreases. So we also are going to multiply by d theta dt, also known as theta prime. Second, we want to look at the derivative of y over 180. Well, that's the same thing, by the way, as the derivative of 1 over 180 times y, and that's just a scalar times a function. So the derivative here is just 1 over 180 times dy dt, or y prime. So there's the relationship that we're looking at. We want to solve this, though, to figure out what theta prime is, because we're looking for the rate of the angle of elevation, or the rate at which the angle of elevation is changing. So to do that, we need to get theta prime alone, as well as then plug in anything that we know. So I'm going to do the theta prime alone part first, just because I think it's the most involved. So I'm going to multiply both sides by 1 over secant squared of theta. When I do, though, this creates, it simplifies the left side, so we just have theta prime. It does create some issues on the right side. Specifically, a couple pieces here. First, secant squared of theta is the same thing as secant of theta squared. And second, if you have 1 over secant of theta, you should know that 1 over secant of theta is equal to its reciprocal, cosine of theta. So in reality, I can write this equation as 1 over 180 times y prime times cosine of theta squared. And so I'm going to do that, because now that we have that ready, all we have to do is substitute in the appropriate values for all the pieces that we have here. So for instance, y prime. As I look to evaluate y prime, I point out that y prime is the rate at which Spider-Man is climbing, and that's just positive 7 feet per second. So we're going to have 1 over 180 times 7 feet per second. Then second, we've got to do and multiply by cosine of theta squared. And you might feel for a second that cosine of theta is nowhere to be found. It's certainly not given to us. But remember, cosine is just equal to adjacent over hypotenuse. And we know that the adjacent is always 180, and at this instant, the hypotenuse is 212. So we actually end up with 180 over 212 squared. And this is absolutely the value we're looking for. And technically we don't have to simplify it, but it's always nice to simplify where you can. So a couple little pieces here just to clean up the work I'm going to do. This is 7 over 180 times 180 squared over 212 squared. So notice that the 180s, one of the 180s divides out, and you're left with 7 times 180, which I could simplify if I wanted to, but I don't really want to, over 212 squared. And for the sake of completion, let's get what that number is numerically. 7 times 180 divided by 212 squared. So 0.0280. I have 0.028, is that right? Yay! So there is our numeric answer. The only thing that's missing is, of course, our units. Well, we know that everything is changing relative to seconds, like we're talking about 7 feet per second, and we plugged in fact, 7 feet per second. So it's going to be something per second, that's for sure. But the question is then, what are the units of theta measured in? We're talking about how an angle is changing. We need to know what its angle units would be, or angular units would be. Well, for angles, when we differentiate using those nice trig rules, we have to use the period of pi. In other words, we need to use radians. So this one actually becomes radians per second. And voila, there is our answer to 14C. Now something is interesting here, and since I'm in control of these videos, and I'm doing everything that I feel like is appropriate, not necessarily just the minimum of going through the problem, I figured it might be worth pointing out to you and proving, or showing to you. I won't be able to formally prove it unless I did all 6, but showing you that it doesn't really matter which trig expression you select, you'll still be able to get to the right answer automatically. So for instance, consider this one. A really common starting point, because it's the first trig function you learn, is sine of theta. And in our particular problem, using those values that are changing, sine of theta is equal to y over d. So again, stick with me for a little bit here. So if we want to differentiate sine of theta over y over d, which looks completely different from our original one, you can see this might take a little bit of time, but we can do it. We're going to get cosine of theta times theta prime on the left. On the right, we have two functions being divided, which sounds like quotient rule to me. In fact, low d high minus high d low, all over low quotient rule. So there's our stuff. We want to eventually again solve for theta prime. And again, this should get us the same answer. If it doesn't, bad things are brewing. So as far as values here to plug in, which we should probably try to, cosine is 180 over 212. So 180 over 212 times theta prime. On the right side, we have d times y prime minus y times d prime. And now we don't have d prime written on this page, but we found d prime before. It's 196 over 53. So 196 over 53. And then all of it is divided by d squared, and d squared is 212 squared. So this expression is what we need to solve. To finish the problem off, though, without having to do all the fancy simplifying, which I don't really feel like doing, and I'm not going to do, I'm going to multiply both sides by 212 over 180 to isolate the theta prime. So there it is. That gives us theta prime equal to, well, I can see the 212s, one of them is going to divide away. Everything else looks like it's sticking around, so I'm not going to say anything. I'm just going to let it play out. Let's see, 212 times 180. And then the magic part is if we put this in the calculator, we should get exactly the same number we did before. So math fraction 212 times 7, minus 112 times 196 over 53, all divided by 212 times 180. And notice that we once again got 0.028034. Good job, us. We were able to get it there. And again, the moral of the story is it doesn't matter which trig ratio you choose, as long as you do your differentiation correctly. You'll be able to get to the correct answer through any of those 6 paths. Okay, that brings us next to question number 15. And question number 15 continues the Avengers theme story, or the old Avengers theme story. It says that Tony Stark and Spider-Man have an argument and go separate ways. From the building where he is climbing, Peter swings off heading due north at 36 miles per hour, while Stark flies off due west at 70 miles per hour. So let's picture this. Assuming that we have north, east, west, and south, it says Peter is going this way, and it says Stark is going this way. So we assume for the moment that Stark must have gotten closer to the building so that way he could have an argument enough to storm off in the other direction. So right here, we know how fast each of these are changing. Stark is going 70 miles per hour, which, I mean, knowing Stark's nature, that's probably a restrictive, or he's holding back. What's his face? Spider-Man is going 36 miles per hour, due north. And of course that means that there's a distance between them, and naturally that's what the question is probing for us. Is they're asking at what rate is that this distance, which I'm going to call d, changing. At that instant, when it says Peter is 40 miles per hour north of the building, so that's 40 miles. And then Tony is 30 miles west. So we know all that stuff. So that's what we were given. That's the diagram that we can set up based only on the given information. And that means then it's time for us to do the rest of the work ourselves. So in looking here, they've given us snapshot lengths for both Tony and Spider-Man, but it's important to remember that both of those are changing. Clearly, if one's going 36 miles per hour and the other's 70 miles per hour, they are very much changing. Those two particles, in this case Spider-Man and, let's say, Aquaman, Iron Man, are both moving. So what I'm going to do is I'm going to give them a variable name. I'm going to call this X, and I'm going to call this Y. You'll see it's a pretty standard convention in math, not to mention when I'm doing it. And that's natural, just to call them X and Y, since we already have a conception of horizontal being X and vertical being Y. And then based on the information that we're given, if we have a 30-40 right triangle, the third side has to be 50 miles. So I'm not going to spend much time using the Pythagorean theorem to get there. I just recognized the special right triangle. So I ran with it. So given that information, our next move is to start to relate everything together, because we want to figure out how fast the distance between them is changing. How fast are they, quote-unquote, moving apart? So to do that, I'm going to start with the relationship that governs those three sides. We have x squared plus y squared equals d squared. And from there, I want to take the derivative with respect to time. So that's going to give me 2x x prime, or 2x times x prime, or dx dt, plus 2y times dy dt, or y prime, equals 2d times d prime, or dd dt. So just like before, all the 2's divide away. We've got xx prime plus yy prime equals dd prime. So a pretty straightforward one to go through. Now it's just a matter of us plugging all the information in directly from the problem. So for x, we know that that's 30 miles, and we know Tony was traveling at 70 miles per hour. So that makes sense. And his distance is getting bigger, by the way. So we don't want to call it negative, even though it's moving in what we might normally call a negative direction. Like, since it's getting longer and further from that point, we do want it to be positive. Next, we want y prime. Well, y is 40 miles per hour, or y is 40 miles, excuse me, and the speed of Spider-Man is much lower at 36. Then finally, for the distance, we know it's 50, but we want to figure out what d prime is equal to. And this is a good starting spot, because now we can finish this off. It's actually not a good starting spot, it's a good finishing spot, really. Looking at these pieces, if we put 50 in there, we can divide out the 10 from each individual term. We're going to have 210 plus 144 all over 5. And 354 over 5 should not simplify. It's like 70.8. Actually, it is 70.8, isn't it? It's kind of cool. We'll just leave it as an exact decimal, because why not? 70.8, and this is the rate at which that distance between them is changing. In our units, we're talking miles per hour, so I'll put mph there as well. And there's our answer to 15. It's actually a very basic question, but some things that can catch you, typically that like directional part, like a lot of people see Tony Stark going west as being negative as far as rates of change, but of course, since that length is getting bigger and bigger as he moves further and further west, forces this thing to instead be positive all the way through. Okay, that next brings us to 16. And 16 is the first problem we're going to hit involving what I call the shadow problems or the similarity problems. So in this situation, it says 6-foot-tall Ryan is walking away from a streetlight along a straight line path at 4 feet per second. If the streetlight is 15 feet tall, at what rate is Ryan's shadow lengthening? So to help us visualize this, I want to draw the situation out. I'm going to start with the streetlight. I don't actually know exactly what streetlights look like, but I imagine they look something like that. So there's the streetlight, and they're telling us the streetlight is 15 feet tall. Now I don't know everything about streetlights, but I feel pretty confident that a streetlight is not going to change its size. So I'm going to straight up mark it as 15 feet and assume that it's not changing at all. Next, we also have to take into account 6-foot-tall Ryan. So we'll let this be Ryan right here. He's walking. Looks like he's probably reading his phone if I'm looking at my picture itself. Close enough. So there's Ryan walking. And it's talking about his shadow. So now we have to think about this a little bit. So to help me, I'm going to use this yellow line really fast, and then I'll erase it afterwards. So the light shines in all sorts of directions here. But if we think about it, treating this as like a point source of light, the light's going to shine this way, and when it hits Ryan, it's going to cast a shadow. That shadow is part of the situation we're looking at. Oh man, I lost his phone. Huh! His phone got flattened. Close enough. So basically that shadow is part of the work that we're going to do here. So to help us with that, let me choose a color that's slightly warmer. Let's pick a warm orange light. I'm going to go ahead and mark it. So basically there we go. There is the light shining down, which creates, of course, that shadow, and creates a right triangle involving this Ryan that we're analyzing. So there is 6-foot-tall Ryan. And then second, you may not see it at first, and it may seem like a weird one to think about. We also have to consider this length right here, because that length is the distance from Ryan to the street lamp. And basically as he's walking away, because it says he is walking away from the street light, he's moving in this direction, making that length larger as well. So we actually, in fact, know that he's walking from that streetlight at 4 feet per second. So we actually know that rate of change. So we need something that describes this guy so we can look at how it's changing. So with everything in there labeled so far, what we can next do is we next want to label everything that's changing with a variable, so that way we can take it into account and differentiate with it. So in here, I'm going to call L the length of Ryan's shadow. Length of shadow. And again, you maybe never have looked at this, but the further you get away from a light, the longer your shadow becomes. You can actually see why in this picture. If we put him further out, he'd be the same height, but it'd have to stretch a little further. Obviously, intensity decreases, but whatever. And then if that's the length of the shadow, I'm going to call this little distance D. And actually, D is probably a bad choice. I'll use capital D. D is distance from light. So how far away Ryan is from the light. And keep in mind that Ryan is walking in this direction, so as he does, the dimensions of the triangle are going to change a little bit as well. Really? It's not going to let me do that. Okay, well, I was trying to make it shown, but whatever. So that's where we're setting up. So for clarity's sake, let me redraw this really fast for us. I want to draw it as a purely geometric construct. Right now it looks like a pterodactyl's head. It's not what my goal was. So there's our triangle. There's Ryan. This is 6. This is 15. This is D. This is L. And I should have mentioned it before. We assume the street light is perpendicular to the ground. Otherwise, someone's got to get the utilities or the city out there to repair it. So with that in place, this is now our place to work from. The strategy I'm going to advocate here is called similar triangles. And I say similar triangles because what we have are two triangles that are scaled copies of each other. Because this one over here also has to be a right triangle, and it's got to be proportional to the first one because it's literally a part of it. Whatever the angle is here, they actually share that angle. And by they, I mean this smaller triangle and this bigger triangle. They actually share that angle, which means that the two are proportional. So given that, to set up a similarity triangle or a similarity statement for these two triangles, you've got a couple different options to do. I'm going to go one triangle at a time. So basically, first I'm going to look at the little triangle. The little triangle has L and 6, so I'm going to write the ratio there as L over 6. And then second, for the other triangle, I'm going to use the big one. So again, it might be kind of hard to see, but the big one will be the one all the way on the outside. The big one is going to be the horizontal distance, which in our case is D plus L, over the vertical distance, which we have is 15. So with this in place, this is the equation we're going to have to differentiate. This contains all the information we need to know about how these lengths L and D are related, the distance from the lamppost and the length of the shadow. So to work from here, we are going to have to differentiate, but my recommendation to you is to start by doing some algebra on it first. So for the algebra portion, I'm going to multiply both, or I'm going to cross multiply both fractions. So it's going to give me 15L equals 6D plus 6L. And the reason I bring that up is that it allows me to combine some stuff together really nicely. This becomes 9L equals 6D, and so that gives us a nice relationship to work off of. Now, as far as the pieces here, you might start to ask yourself, well, shoot, I don't know what L is and I don't know what D is. They didn't tell us how far they are. They just told us how tall the street lamp and Ryan were. Well, the reason that that's okay is that we don't need to actually know the specifics. All we need to be able to do is differentiate this thing with respect to T. Because what we've done is we've related the length of the shadow to the distance from the lamppost. So now, to capture the rates of change, we just differentiate with respect to T. So this gives us 9L prime, or dL dt, equals 6 dd dt, or d prime. As far as these ingredients, we're looking to solve for the rate at which shadow is increasing. So the shadow is L. We do know that Ryan is walking away from the street lamp at a straight path at 4 feet per second. So that means this has to be 4. So we're going to get 9L prime equals 6 times 4. And from there, we can divide both sides by 9. We'll get L prime, also known as dL dt, or the missing things derivative at this time, is equal to, let's see, that'll become 2 over 3, 8 over 3, which is code for 2 2/3. Yep. And then as far as units, we're talking about how fast the shadow's length is changing. That would be measured in length units per time, which in our case would be feet per second. There it is, a little bit, 2/3 of the way from 2 to 3. So it's not moving very fast, and obviously if you've ever walked with a shadow kind of casting out in front of you, you see it doesn't grow that fast, but it is growing for sure, thanks to the presence of those streetlights. Okay, that brings us to question 17. I think I'll have to take a short break after this one. So this is based on Parks and Recreation, likely my favorite show of all time. I'm actually right now in the middle of rewatching the entire series start to finish, for I believe it's the 9th time. So I'll just have it on when I'm on the treadmill, have it on while I'm eating dinner or working on something. So in 17, it says, after being inducted as mayor, Gary was sent into the sky above Pawnee in a hot air balloon. After a few glorious minutes in the sky, Gary's balloon begins to descend towards the ground at a rate of 5 feet per second. Wanting to greet her friend, Leslie begins to walk toward the balloon's launch point at 2 feet per second. At the instant when Leslie is 28 feet from the launching point and Jerry is 45 feet from the ground, at what rate is the angle of elevation from Leslie to Jerry changing? Wow, that's a lot of words, isn't it? It is. But that's okay. We can set this up. So trying to picture what's happening here, we got a lot going on, but we definitely start by having a hot air balloon with Gary, Larry, Jerry, Gergich, Gingrich. Yep, that's a terrible looking hot air balloon. I need to fix this. Let me draw a better hot air balloon. Okay, there, we'll start it over here. So hot air balloon. There we go. Looks like how I used to draw elephants, actually, when I was a kid. So there's our hot air balloon. I know I can give it some cool design. So there's the hot air balloon. They tell us in the problem that the hot air balloon begins to descend towards the ground. While it's descending towards the ground, we have Leslie Knope over here. And Leslie begins walking toward the balloon's launch point. So Leslie's walking in the direction of the balloon. So if we try to picture all of this, they're talking about angle of elevation as well, so it's something to consider. Basically what we've got is another Pythagorean relationship. In fact, I think this one was only thrown at the end because I wrote it later because I felt like you needed more practice with it. So there is our triangle. Now as we start to think about this, before we start to plug in information and details from the problem, let's point out here that actually there's a lot of things changing in this problem. First, since the hot air balloon is going downward, the vertical distance is changing, so I'm going to assign it the variable x. Horizontally, Leslie is moving closer and closer to the hot air balloon, which means the horizontal distance is changing, and in fact it's decreasing. So that one would be x as well. Finally, the distance of the hypotenuse, since both the other two legs are changing, that distance should also be changing, so I'm going to call that the variable d. Beyond that point, we next want to look at the snapshot moment, as in what's actually happening at the instant we're measuring. And in looking in here, we have Leslie is 28 feet from the launch point. We have Jerry, Larry, Gary, Gingrich, Gergich is 45 feet above the ground. And of course, we're looking for the angle theta. So we are going to have to figure out what theta is equal to. I should have given that a variable name before. And then last but not least, we don't know what d is right now. We need to include it in there, but we can find it really fast using the Pythagorean theorem. Just trying to see if there's a way to do that really fast. So it equals d squared. So pulling out our graphing calculator one more time, we're going to have 28, that's 228. 28 squared plus 45 squared. And then we're going to take that to the 0.5 power, or square root it, and we'll get 53. Cool. So d is equal to 53. We can put 53 on the inside. So in this case, it's not really the setup that's different. The setup here isn't too bad. And in fact, you can probably already tell that what we have is a Pythagorean problem. The difference is in this Pythagorean problem, both of the legs, as well as the hypotenuse, are all changing. So our relationship to start here is really x squared plus y squared equals d squared. It's not like the Tony Stark and Spider-Man problem where one of those pieces was constant, so when we differentiated it went away. We're going to need to consider all three of these things derivatives. So at this point, we're ready to differentiate though. And again, we're going to do it with respect to t as always, since that way we can tell how fast things are changing over time. Our derivative is 2xx prime plus 2yy prime, or dy dt I should say that, 2 big D times d prime. And once again, the 2's divide away, so we're just left with x prime plus y prime equals d prime. Okay, so from here, we're looking at all the ingredients. We want to plug everything in. Now this problem isn't a perfect one because it doesn't come out as interesting as I'd like it to. But in fact, we should consider the fact that since Leslie is walking towards the balloon, and since Jerry is going down, that means that our triangle is getting smaller vertically and smaller horizontally. So what we should have is we should make sure to have x prime be less than 0 and y prime be less than 0. They should have negative signs. In this particular problem, it won't hurt you, but there are situations where it will, so you got to be careful. So in looking at our problem here, we already can plug in some of this information. X is 28, and x prime is the rate at which Leslie is walking. And it says Leslie begins to walk toward the balloon's launch point at 2 feet per second. So it'll be x prime is negative 2. Negative because it's going towards the balloon's landing spot and making horizontal smaller. 2 because they told us to. Next we've got y. So Jerry is 45 feet in the air. Y prime is the rate at which Gary is descending, and it says that he is descending toward the ground at a rate of 5 feet per second. So that's going to be 45 times 5. And all this is going to be equal to... Wait a second, I'm not even doing the right problem, am I? Why didn't you stop me? Jiminy Christmas. So yes, all this work would have been good, but that wasn't actually what we were interested in here. We were interested in dealing with the angle of elevation. We wanted to look at theta's rate of change. So we don't need to do all that work. We want to instead look at how theta is changing. So in here, here's the big thing. We would have actually needed that work if we chose a ratio involving d, because we don't know how fast d is changing. But in our particular problem, because we know what x prime and y prime are, we just said that y prime is -5 and x prime is -2. We can actually jump right in here and do this using using those ratios. So what I mean is I'm going to choose to include y and x both in my trig ratio, and the trig ratio relative to theta that uses y and x is of course tangent. So tangent of theta is equal to y over x. From here, I can go ahead and take the derivative with respect to time on both sides. So from there, we're going to get secant squared of theta times theta prime, because remember our ultimate goal here is to figure out what rate theta is changing. On the other side, we have y over x, so we're going to need to use the quotient rule. So low d high minus high d low, all over low quotient rule. There's our stuff. At this point, we can plug in everything that we need, although I like to simply multiply both sides by 1 over secant squared first. That's just kind of a personal choice, but it's always been a favorite of mine. Of course, the reason I do that is, like self-serving, 1 over secant squared is cosine squared. So really this is going to be that big fraction times cosine of theta squared. That's just what 1 over secant squared is equal to. As far as the ingredients here, x is 28, y prime is -5. I even had a mistake over there on that other side. Then we have minus y, which was 45, times x prime, which is -2, all over x squared, so 28 squared. And all of this is being multiplied by cosine of theta, and cosine of theta is adjacent over hypotenuse, which in our case is going to be 28 over 53. And for the sake of simplicity, I don't want to go through and actually calculate out, or I guess I will do it. For the sake of completion, let's do it this way. So as far as stuff here, I'm not going to use the fraction this time. We'll go 28 times -5 minus 45 times -2. All of this is divided by 28 squared, using the extra parentheses just to make sure. Then we're going to multiply the entire thing by 28 over 53 squared. Combining all that together, we get that our answer is -0.0178. And of course, we don't need quite that many decimal places, so we could be a little bit shorter. Technically, I think it's this. If we go with an equal sign, we could instead say theta prime or d theta dt is approximately equal to -0.018. And as far as units, we're talking about an angle of elevation, so angles are measured in radians. And as far as time units, we were talking about feet per second a bunch of times, so it should be radians per second. There is our answer to question 17. Okay, question number 18. So it says a large cylindrical vat of radius 8 feet is being filled with water. So basically, translating that down a little bit, it's like someone's got a cylinder-shaped cup and they're pouring water into it. The rate at which water enters varies over time according to the function e of t. So it says the rate is e of t. So it's kind of like e is the derivative of something. Assorted values of the rate e of t are given in the table below. So the table is giving us some stuff. It says first for 18a, at what rate is the height of water in the vat changing at time t equals 7? So the rate at which water enters varies over time. We're in a cylindrical vat. We want to figure out what rate is the height of water in the vat changing at time t equals 7. So in order to do that, we're going to need to figure out a volume equation. Because weird as it is, e of t is actually the equivalent of v prime. So and the reason I say that is simply that, looking here, look at how it's measured. E of t is measured in feet cubed per hour. That's a volume rate of change. And it says hour here. I got to make sure I've got the minutes right. I think this is hour per minute, sorry. So that's feet cubed per minute. And then over here they're giving us the rate of change of the volume. So what we need right now is a volume equation. So the question is, how do we write that volume equation? And unfortunately, I failed to give you the equation for a cylinder's volume in this case, but we've done it before. So I can tell you right now that the volume is pi r squared h. As we said before, it's like setting a circle down and stacking a h heights worth of circles on top of each other to get that exact volume. So in here, if v equals pi r squared h, the first thing we want to do is see if we have any information we can plug in right off the bat. And since this is a cylinder, the radius does not change. So that means we can automatically let r equals 8 without having to worry about whether or not we're snapshotting too early or not. So specifically, this is going to lead us to the equation v equals pi times 8 squared h, or that v is equal to 64 pi h. So again, we can do that because cylinders, here's a cylinder for us to look at. Cylinders have a constant radius. No matter where we draw the radius, it is identical, well, except for when you draw it poorly. The radius is 8 everywhere. So basically, given that, we now know that v is equal to 64 pi times h. And that means it's time for us to go ahead and differentiate with respect to time. So we're going to ddt this equation. When we do, we get dv dt is equal to, well, it's pretty clean, 64 pi times dh dt, or h prime. So there's the equation we're looking at. Now, as far as information there provided, remember we said that E of t is the equivalent of v prime. It's telling us the rate at which water is entering the tank, or the vat in this case. So basically what we're looking for here is we want the volume's rate of change at time t equals 7. Well, that's going to be the equivalent of E of 7. And that means E of 7 is going to be equal to 64 pi times h prime. Well, finishing this up, wrapping this up a little bit, E of 7, it says right here, is 2.485. We're going to, if we want to solve this, we're going to have to divide both sides by 64 pi. So 2.485 divided by 64 pi is going to be equal to h prime, or dh dt. And that means for our purposes, dh dt is going to be equal to whatever that quotient comes out to be, 2.485 divided by, and be careful if you divide this, make sure you either use the fraction creation or that you put parentheses around the denominator. You'll get a correct answer of 0.012. And since we're talking about height here and we're talking about feet cubed per minute, this should be feet per minute. There we go. There is 18A. 18B then says, if the height is changing at rate h prime of t equals to that thing, at what rate is the volume changing at time t equals 5? So we're starting in we have slightly different information this time. You can consider it as we discovered something different about the problem, or we decided to approach it from a different direction, vary something else, who knows. But basically our setup is still the same because we still have the same large cylindrical vat that has that same constant radius of 8 feet. From here, what we need to look at, and we won't even need the table in this case, like in fact we won't be able to use the table anymore, so we can dump that for the moment. If that's the volume, we again can differentiate it with respect to time t, and unsurprisingly we'll get dv dt is equal to 64 pi times dh dt, or h prime. They're telling us right now what h prime is equal to, so while we search for v prime, we know that v prime is going to be equal to 64 pi times h prime of t, and h prime in this case is 1 over 59 square root of t plus 2.3 sine of t. But remember, we're doing this all at t equals 5, so I'm going to go ahead and plug that in. We'll have square root of 5 plus 2.3 sine of 5. And so this will give us our volume's rate of change at t equals 5. So once again, we can say that dv dt is going to be either equal to exactly what's there or approximately equal to whatever this comes out to be. So we'll go 64 pi divided by 59. All that stuff times the square root of 5 plus 2.3 sine of 5. And it tells me that our volume's rate of change in this case is going to be 5.697. And we're talking about feet cubed per minute. And there we go. No, just really fast, in case you missed it. It should say minute, so we'll fix that on the notes, or in the assignment. Okay, this brings us to question 19. And question number 19 is the standard cone question. I've just broken it up into pieces to hopefully make some pieces a little bit clearer for you. So we've got a right cone-shaped container that holds a chemical mixture. Seems like a terrible choice. Maybe it's some sort of fancy New Age beaker or something. The cone is 12 inches tall and has a radius of 2 inches. The cone is initially full, but liquid drips out of the cone at 0.3 inches per hour when the height is 5 inches. The volume of the cone is pi over 3 r squared h. Pretty standard stuff. So to help us here, I'm going to draw a picture of our cone first. Slanted a little more than I'd like it to, but there is our cone. Drawing that nice perpendicular area in there. Those are perpendicular to one another. That is our radius, and this is our height. So basically there is the cone itself. As far as information they do tell us that the cone is 12 inches tall, and they also tell us that the radius is 5 inches, or excuse me, 2 inches. So actually I probably should have made this taller and thinner, but close enough. And of course they tell us our volume formula. So the first question we're asked here is question A, how much of the chemical mixture is in the cone-shaped container when it's full? That's just a matter of plugging in the information into our volume formula. The volume at this instant we're analyzing the cone is going to be equal to pi over 3 r squared times h. R is 2, h is 12. As far as values here, we end up getting 48 pi over 3, or also known as 16 pi, and it should be inches cubed. So there's 16 pi inches cubed of liquid in there. That should be somewhere around 50. I like to have a number somewhere, 50.265 inches cubed. So there we go. It helps to have that correct answer somewhere nearby. So that's part A. Part B asks us then to write a similarity statement for the cone's dimensions. And this one definitely can throw people sometimes. And it takes a little bit of getting used to, but the nice thing is once you've mastered it for a cone, it is always the same. So I want to imagine for a second that we have only this much liquid inside there. In other words, we have this purple cone that has a height of 12 and a radius of 2. We have the smaller red cone that has a height of some smaller amount and a height of some, or a radius of some smaller amount. So typically what you'll see is you'll see an expression like this set up. They won't mark those as r and h, and I definitely wouldn't. Instead, they'll mark this little distance we just created as h and r. That way we can look at those ones and think about it as the red cone is constantly changing its dimensions. But the nice thing is, if we look at this cone, it's totally proportional to everything on the original purple cone that we had here. In other words, if the height was 6, the radius would be 1. Each one would be half of what they started with. If the height was, 3, that's a quarter of where it started, we would have 1/2 for our radius, because it would then have to be a quarter of what was there. That's because these two pieces are what we call proportional, or the two cones are similar. So in order to do that, we set up a similarity statement that allows us to connect the two cones together and ensure that r and h have a proportionality or a scale working together as you move through the problem. So what I mean is this. Let's just look at the ratio of r over h. That ratio is going to be the same everywhere, even as r and h change. Or better put, as r changes, h will change proportionally too. And that proportion is equal to the original arrangement of our cone. So in looking here, r and h are proportional to the 2-inch and 12-inch original starting pieces respectively, which means r over h is going to be equal to 2 over 12 at all times. That is the proportion. The radius and height will always be in a proportion of 1/6 with one another. So what that tells us is for part B, when we're asked to just write the similarity statement, that's going to be equal to 1/6. So part B, pretty simple, but a really essential piece to capture how that original marking of the cone or the original dimensions of the cone inform the proportion of those smaller cones as liquid either leaks in or starts to fill the cone. Okay, third, that brings us to part C. Part C asks us to solve the similarity statement for R and make a substitution to write V fully in terms of R. Again, this is just all training you to what your work's going to look like when you get to this problem in a future problem. So we start with R over H equals 1/6. If we solve for R, we would have to multiply both sides by H. When we do, we'd get that R is equal to 1/6 H. Now that's a huge starting spot. We just solved it for r. Now it says to make a substitution to write v in terms of r. Or it should be v in terms of h. I apologize. That was what we were looking at there. Another small mistake. So r is 1/6 h. So from here, what we want to do is we want to take our original equation, which is v equals 1/3 pi r squared h, and we want to plug in the 1/6 h for r. When we do, we'll still have 1/3 pi. R will be replaced with 1/6 h, and then of course r squared times h. And from there, it's just a matter of simplifying everything. We're going to get 6 squared is 36 times 3 is 108. We're going to get 1 over 108 pi times h squared times h to the first, which is equal to h cubed. And so this is our new volume that is purely a function of the height of the cone. And again, this is just purely a choice. We could have obviously chosen to instead solve for r and h. It's just a matter of what we're being told. And since it tells us well, let's look at the next part. Since it tells us that we want to find the rate at which the height of the cone is changing, it would be really helpful for us to instead have the volume in terms of h. So in fact, in preparation for the last part, I'm going to steal this. It's my name after all. I'm going to steal that piece and bring it over. And from here, I'm now going to go ahead and do what part D says, which is find the rate at which the height in the cone is changing when the height of the liquid is 5 inches. So for our purposes, that's a pretty clean thing to do. I'm going to differentiate everything with respect to t. So digging into there, we'll of course have v prime. We'll have 1 over 108 pi. That's not changing. And then we'll multiply it times 3h squared. And then of course, by the chain rule, and because h is changing, times dh dt, or h prime. So from here, we've got to plug in all the information that we have. So some stuff to point out is we know that the height of the liquid in the cone is 5 inches. Actually, I'll change some colors here. We know the height of the liquid in the cone is 5 inches. So looking in here, that means we're going to be able to plug it in right there. So this is going to be a 5. We also know that liquid is dripping out of the cone. Where is it? Let's go orange. We know that liquid drips out of the cone at 0.3 inches cubed per hour. I don't know what that is for. So that means that we're going to be able to plug that in for v prime. And then ultimately that'll leave us with just a single variable of h prime for us to solve for. So executing these moves, we know v prime, it's dripping out of the cone, so I'm going to say 0.3 as negative. On the other side, we have the pi over 108. We have times 3. H squared was 5, or h was 5, so 5 squared times h prime. So digging some ingredients here, a couple different things to see. First, 3 over 108 is just 3 over 36, so that'll just clean our work up a little bit. We're going to have negative 0.3 is equal to 25 pi over 36 times h prime. And last but not least, that's going to allow us to solve this equation pretty nicely. We're going to get h prime equals negative 0.3 times 36, all divided by 25 pi. And now, as I mentioned before, when you put this into a calculator, make sure you have parentheses around the denominator, or that you use the fraction button itself. Calculator doesn't know what you're thinking. And from here, we'll get negative 0.3 times 36 divided by parentheses 25 pi. And that gives us our answer of it's negative 0.318. 0.138, excuse me. So this is the rate at which the height is changing, so that would be in inches per hour. So there is our work. I would say that is our great answer. You could also say something, because that negative sign, sometimes that messes with people, you could also say that the height is decreasing by 0.138 inches per hour. Both answers would be perfectly acceptable, and in fact I probably wouldn't hold you to the negative sign in this particular problem, since it really just asks the rate at which. It doesn't ask you to interpret it all. But there's your work. So again, the big stuff to draw out of this first cone problem is specifically that we began by figuring out the similarity ratio, or the similarity statement. So in other words, we found the proportion between the radius and the height. We solved for r as a function of h, so that we could substitute it into our volume to get everything in terms of h, since we're ultimately going to be asking about the rate of change of h. Then finally, we differentiated our new equation. There was only one variable on each side, and we solved for the missing piece, just like we have so many times before. Okay, that next brings us to number 20. So number 20, based on a true story, although I think I was actually at a math contest, supervising or chaperoning a math contest that day, so I didn't see all this happen, but forgive that. So number 20, after lots of false starts, Mr. Steele finally starts transforming the backyard. The contractors bring in a truck and dump river rock in the yard, forming a wide conic pile. So conic pile, I should probably say conical pile now that I think about it. Wide conical pile. It has a radius that is double its height. So R equals 2H. And then second, because of the fact that we're talking about a cone-shaped, that's really what this means. This means cone-shaped. Since we have a cone-shaped pile, that means that we're going to need that volume formula for a cone. So we just used it a second ago, so I'll just put it in here. Again, I could have printed it on this problem again, but I felt like it was close enough in there. I observe that the height of the pile is growing at a rate of 1.3 feet per minute. So in other words, h prime, or better yet, dh dt, is equal to 1.3 feet per minute when h equals 5 feet. So look at that, just reading straight out of the problem, one after another, drawing all that info out. Finally, we are tasked with finding the rate at which the volume changes when the pile is 5 feet tall. So actually a pretty standard question. And the thing that makes this problem a little bit nicer than the previous one is that they actually gave us our similarity statement right away. It might not have jumped out at you right off the bat, but by telling you that r is equal to 2h, that the radius is twice as large as the height, meaning that this cone-shaped pile is fairly wide. There's what our cone would look like, with all the rock forming on top. So by telling us that, they actually saved us the trouble of having to go through and actually solve for the similarity statement. Instead, we can use that information right away to just plug into our volume. So in particular, I'm going to do that first. Now I have 2 pi's there. I apologize. Normally a baker would not have to apologize for having 2 pi's, but a mathematician would. So pi over 3 r squared h. So plugging in here, we have pi over 3 r squared h. Looking in, that's going to simplify and give us a volume of, looks like 4 pi over 3 h cubed. So there's our volume equation. That's the new one we're going to use. We now want to start to look at the rates of change for that equation. So we're going to ddt it. Looking at our ingredients here, we'll get v prime equals 4 pi over 3 times 3h squared h prime. The rest of this problem is pretty familiar. So in looking here, they did tell us that h is 5, so we can go ahead and prepare to plug that in. They also told us that the height of the pile is growing at a rate of 1.3 feet per minute. So that's our dh dt, or h prime right here, that we're going to be looking at. So we can also plug in the 1.3 right there. When we do, we get v prime, or dv dt, is equal to, well, a couple different things to clean up. We'll have 4 pi times 5 squared times h prime, which is 1.3. Simplifying a little bit, we get 4 pi times 25 is 100 pi times 1.3. That's going to be equal to 130 pi. And just checking to make sure I did do that correctly. I did. 130 pi is going to be our dv dt, the rate at which the volume changes with respect to time. So how quickly rock is being dumped into that conical pile. And as far as units, we're talking volume, so that's going to be feet cubed. And as far as time, we were talking per minute. So there is our answer. So rock's coming in pretty darn fast, especially because it's feet cubed per minute. So I mean, if you go 130 times 3, that's like 400 cubic feet per minute. Yeah, it's probably a big pile. Might have poorly identified the units for this problem, but for the moment, maybe it was only for a short time. So with that said, there is question 20. Okay, the last thing we're going to hit here, and this will take a little bit of time to work our way through. So we're going to work through an old problem that we had and that I used and wrote in, I think, 2012 or 13, which is called the Big Spoon, Big Problem. Or the Big Spoon, Big Problems, Big Problem. So in this case, this is a related rates problem that involves some different connecting rates in kind of a unique way. So there's lots of stuff in here. I'm not going to read you the problem. I'm just going to kind of work through the pieces simply for the sake of saving time. Otherwise, this would take me a long time, and I don't have pretty pictures ready for this particular problem. So the big thing to pay attention to, outside of the story about Tyler, this was Tyler Blake, an all-time great baseball player at Franklin, who I coached from when he was, I think, 11 or 12. So he decides to go to Big Spoon Yogurt, which is going out of business, and buy a whole bunch of yogurt, and then mail it to himself, so that way he can enjoy Big Spoon Yogurt after it's closed. Now, I would point out that Menchie's is clearly better, and I am not a paid spokesman of Menchie's, just a huge fan. But at the same time, there's some ingenuity in this completely, not to mention the fact that it's just a plain box. So basically what we have here, first and foremost, is that he's going to be putting the yogurt into a large, flat rake, rectangular box with a 12 by 12 inch square base and a height of 6 inches. So the first question we're asking here as well, by the way, A, is what is the volume of the large flat rate box Tyler has? Well, if I draw out what that box might look like, give or take a few post office logos and insignias, the box is going to look something like this. So there's the box. He's going to fill it with yogurt. So I don't know how to draw yogurt. I don't know. Except it's going to be filled with the liquid yogurt the entire time. So the box is in there. It says it's a 12 by 12 with height 6. And this is all measured in inches, which is actually a fairly reasonable. I think this might actually be an authentic box size that you can purchase. So it's basically 1 foot by 1 foot by half a foot. So, and he filled it with Big Spoon yogurt. Can you imagine working at the yogurt store when some very tall person walks in and decides to just fill a post office box with yogurt? It's going to be expensive, actually, too. Although I think they really get you on the toppings, but it's a story for another day. So then he returned to the post office and shipped it to himself. So we'll deal with the movement in just a second. So our first question is, what is the volume of this box? Well, since it's a rectangular box, or what we might have called in geometry a rectangular prism, the volume is what you probably remember as length times width times height. So in our case, that's going to be 12 times 6, which is 144 times 6. You can tell I'm just kind of buying time here. I'm just going to ask the computer for that. 144 times 6, which is 864. So there are 864, and we're in inches, I think, so cubic inches of yogurt in there, assuming he filled up every single cubic inch of space in that post office box. Okay, the second part, part B, find the rate at which the liquid yogurt exits the box. So we got to look at our second situation here. So in the problem, it says 1 week later he received the package and the yogurt had melted. Yeah, because that's what yogurt's going to do. And it started to leak out from the bottom. I'd be surprised if it didn't do that before the post office delivered it. So Tyler observed that the height of liquid yogurt was falling at a constant rate of negative 1/2 inches per minute. So the height was falling at rate negative 1/2 inches per minute. So I'm going to go ahead and put that in there. H prime equals negative 1/2 inches per minute. So I'm kind of going back to that inventory style here. The entire situation would have been a mess except Tatiana was there. Okay, that looks like a future part of the problem. So we know the rate at which the height is changing. So you might ask then, well, where do we even use this? Like, what is this? Well, it's exiting the box, which means that we're talking about the height inside that box. So imagine for a second that Tyler, instead of purchasing a cardboard, paperish kind of box from the post office, had purchased from them some sort of transparent box where we could see the liquid yogurt. So what we've gotten here is we've got yogurt inside the box. And because it's dripping out, that height of yogurt in the box is... Oh, come on, really? It's not going to let me do that. Watch this. Here. I just think this is a really essential piece. So, yeah, come back. Okay. So what's going to happen is as that yogurt leaves the box, Jiminy Christmas. There we go. As the yogurt leaves the box, the amount and the height of yogurt in the box is going to slowly decrease. So strangely enough, this is actually a problem we've seen before. We just haven't seen it involving a rectangular prism. This is actually just like our cylinder problem. The base dimensions, which were 12 inches by 12 inches, are going to stay constant. It's our height of liquid that's going to change as the yogurt drips out and decreases the height in the box. So if we think back to our equation, we had volume was equal to length times width times height. In our case, length and width, if we want to call this length and this width, those guys are going to stay constant. We're just going to have 12 times 12 times h as our volume, which means our volume is really 144 h. So there's the equation we're going to be working with. And more than that, we can then take a look at the rates of change. So it says find the rate at which the yogurt exits the box. We're talking about a volume rate of change. not just because that's what it's asking, but also because we were given h prime, so we must be trying to find v prime here. So in our solving, we'll get dv dt is equal to 144 times dh dt. We already found dh dt. The height's falling, so that's negative. V prime is going to be equal to 144 times negative 1/2, and that's going to clearly give us negative 72, and it'd be inches cubed per minute. So there would be our dv dt in this case. So yogurt is leaving pretty darn fast. So that's a lot of cubic inches per minute. It's coming out pretty fast, so it was a really tight box. As soon as he got it home, it just started to go. Maybe he poked a hole in it or something. I don't know. So there is the rate at which the yogurt is leaving the box. Now that's really essential because our next question makes it essential. Part C asks, what is the rate at which liquid yogurt enters the cone? So to describe this part of the scenario, it says the situation would have been a mess except Tatiana was there to catch the ice cream in a really large open cone of height 15 and radius 6. So really essential to get that piece of information. So our picture here, not to keep adding to the diagram, but you know, artist, gotta art. We've got yogurt in here in this box that's dripping out. Tyler's holding it. Let's do a really bad piece right there. Tyler's holding it. And somewhere down here, Tatiana, another all-time great athlete at Franklin. Tatiana Garrett was a soccer player that had a full scholarship to UC Irvine, did great stuff when they won their championship, memory serves. She's holding out for Tyler to help out a cone, and the liquid yogurt is dripping into the cone. Now you might argue whether or not the vertex or bottom of that cone is really going to hold stuff in there, but set that aside for a second. Just imagine the cone's humongous enough so that Tatiana can help out. You'd be kind of scared at that point. So basically there's our scenario. So now the first question here that we're asking with part C is not actually about the amounts, or is not anything super hard. It says, what is the rate at which liquid yogurt enters the cone? Well, think about this for a second. If the yogurt is leaving the cone at, I think it was 72 inches cubed per minute, that same yogurt exiting is entering into the cone. So basically the exit rate is going to equal the enter rate. Simply for the sake of, it's the same freaking yogurt. The yogurt hasn't changed at all. I mean, technically it's melted, but it was already melted. It's the same yogurt. So that tells me that the answer is going to be 72 inches cubed per minute. So it's basically gushing out of the box, but we don't have to worry too much about that. It's basically covering it in. It's the exact same stuff we were dealing with before. Nothing has changed about it. So with that in place, we now know the rate of change of the volume for the cone. So can't get that confused with the V prime from earlier, but we now know V prime for this cone. So let's take that into account. Next asks us to write an equation for the volume of a cone as a function of h. So they're moving us towards the cone world. Well, we said before that V is equal to 1/3 pi r squared h. And then let's look at our cone shapes here to develop that proportionality statement or proportionality and similarity statement. So in here they tell us that the open cone that Tatiana is carrying has a height 15 and a radius of 6. So imagining our cone here, it's got to be a pretty darn big cone really. It says radius is 6 overall and the height overall is 15. That tells me that r over h is equal to 6 over 15. Right? I mean, that's just reading it out of the problem. From there, we can also solve for both sides by multiplying both sides by h. And then we can get 6 over 15 times h is our similarity statement, or our radius as a function of h. And we can simplify that really fast as 2/5 h. So digging pieces in here, we can now plug that into our equation. We'll get that the volume is equal to 1/3 pi times our new r, which is 2/5 h squared times h. And if we multiply this all out, we can clean it up a little bit, make it easier for us to work with. That's 4 over 25 h squared times h. And that should get us to our volume, which is going to be, it looks like 4 pi over 75 h cubed. So there is the volume for our cone as a function of the height. So again, all we've done here is convert this into the same scenario that we had before for our problem with the simpler cones. Now we're ready to analyze the behavior like we wanted. So in fact, I'm going to copy that once more. It's always ready to pose and just move on to the next piece. Are you kidding me? It doesn't want to bring it all. Whatever. There's our stuff. Let's quickly get rid of all this. So for part E, as I erase stuff fiendishly here, part E asks us to find the rate at which the liquid yogurt's height is rising when h equals 5. So again, it might take a second to think about what's happening here. Again, I'm going to go steal my picture of Tyler and Tatiana. I would imagine if they saw this picture, they would be disappointed that my art skills have not developed since they were in my class. They were around me. So in here, and what's happening is, of course, as the liquid goes into the cone, it slowly fills the height of the cone. And so what we want to find out now is, as that little height changes, we want to figure out how fast it's actually changing. And fortunately for us, we know all this stuff. We know how fast the volume's changing, and we know how fast the height is changing, or we're going to find out how fast the height is changing. So that's going to be our goal. So to get there, as you might expect, we're going to differentiate everything with respect to time. So that's been a good strategy for us on, I think, every single problem on this assignment. So take the derivative with respect to t, and give us v prime is equal to 4 pi over 75 times 3h squared times h prime. Can clean that up just a little bit. So we'll get that v prime is equal to 4 pi over 25 h squared h prime. Now as far as our amounts here, what we know, it says when h equals 5. So we're going to be, actually I'll change color. So it did say that h is 5, so that's a huge starting point for us to work with. If h is 5 inches, we can go ahead and plug that in right there. That's a terrible move. We can plug that in for h. That's going to help us out a lot. And second, for v prime, we already found on a previous problem that v prime is that same amount that the liquid yogurt was leaving the box, which is 72 inches cubed. Oops. So v prime is going to be equal to 72 inches cubed per hour. Or was it minute? Sorry, minute. So basically, we've got all the ingredients we need to solve this. 72 equals 4 pi over 25 times 5 squared times h prime. Well, look at that convenience. I wrote this problem intentionally. The 5 squareds divide away. That means that 72 is equal to 4 pi times dh dt. We can divide both sides by 4 pi. At this point, I'll point out that 72 divided by 4 is 18. So that means that we get 18 over pi is equal to our dh dt. As far as units, we're looking for the rate at which the height is rising. So that should be measured in inches per minute. And that's going to be dh dt for the cone that Tatiana sticks out. And if you're looking for actual units, I think I have the units, the decimal version here somewhere, 5.730. So it's approximately 5.730 inches per min. So there's our stuff. So it's rising in the cone pretty fast. I hope it's a pretty big cone. Unfortunately, no, it's only a 15-inch tall cone. So Tatiana's going to have sticky hands pretty soon. It's life. Okay, finally, the last question. How long does it take for Tyler's entire box to empty of yogurt? Oh, shoot, we got 2 more questions. Really? Yeah, well. So how long does it take for Tyler's entire box of yogurt to empty of yogurt? So we've got to think about some stuff here. So what we found first was that the volume in that box was 864 inches cubed. Later, we found, because of the fact that the yogurt was falling at a constant rate of negative 1/2 inches per minute, we found that h prime was equal to negative 1/2 inches per minute. So what that allowed us to do is it allowed us to calculate a rate of change for the volume in there. So we found that v prime was equal to negative 72 inches cubed per minute. And let me just make sure that was the right number because I'm doing this off the top of my head. 72? Yes, it is. Okay, so what we just found was the rate of change of the volume in there. Well, thinking about this, we want to figure out how long it takes something to change or to move out. What we found is a constant rate at which the volume is changing. Right? I mean, it's constant because the height is changing constantly, and the base area here is going to be changing at a constant rate as well, or is just constant itself. So really all it is proportional to h. So given that, what we want to think about is an old equation that I learned back in general science, which I think actually was just eliminated this year. Basically, you might recall distance equals rate times time. So now this was talking specifically about distance, so it is a little bit of a different context, but we can think about it in the context of this problem just by converting it to volume. So this is like saying the volume covered is going to be equal to the volume's rate of change times the time it takes to cover that volume. So in our case, pretty simple thing here. This is 864 is the total volume. The rate it's changing is 72. And we want to figure out how much time it takes to get there. We just have to divide both sides by 72. And when we do that, I believe we get 12, but just to make sure, 864 divided by 72 is equal to 12. So that tells us that it's going to take 12 minutes for the box to become empty. Did I get that right? Yes, I did. So 12 minutes to empty the box. So there's a lot of yogurt in that box, and it's not leaking out too fast. So the problem is how fast the cone fills up, but we'll deal with that in a second. Finally, that brings us to G. Will the cone overflow? I feel pretty confident the answer is yes, but all we have to do is compare the volumes of the two items. We know that the volume of Tyler's box is equal to 864 cubic inches. The question we have is, what is the volume of the cone? Because if we know the volume of the cone is less than the volume of the box, then obviously there's too much yogurt to fill the cone, or for the cone to stay unfilled, so we'd have to go from there. So what we want to do is just calculate the volume of the cone. But did we not already do that? Please tell me we already did. What is the rate? Dang, we did not. Oh well. 4 pi over 75. So we have 4 pi over 75. H cubed is the volume of the cone. We want to evaluate this at the height of the entire thing, which is 15. So I want to evaluate it when h equals 15. So with that in mind, we can just plug into our equation. Let me make sure one more time that we did get it correct. Yes. Okay, that's going to be 4 pi over 75, which, by the way, just for the record, 75 is 5 times 15, so maybe we can make this work a little bit better. 4 pi over 5 times 15 times 15 to the third power. Well, the 15 is going to divide away. This is all just me being lazy, so I don't have to look at a calculator. It's going to leave us with 15 squared, which is, let's see if we can simplify. I'm going to try to do this without a calculator. I'm almost done with this problem set. I want to show off. So it's all over 5. The 5 can be simplified a little bit. So we're going to get instead 4 pi times 45. 45 times 2 is 90. That makes this whole thing 180 pi. So that's the entire volume of our cone. So the question is, what is that value? I'm very confident that this isn't going to be, the cone is way smaller, but let's make sure. It should be around 540, 550, somewhere in that ballpark. 565. So this is approximately 565.487 inches cubed. So unfortunately, volume of the cone is much less, it's probably not that much less, it's much less than the volume of the box, which tells me that the cone will overthrow. Not overthrow, it's not going to overthrow the government, overflow. So in other words, Tatiana, probably ought to go grab some paper towels, or hopefully you have some paper towels handy. So, without further ado, that's turned out to be much longer than I wanted it to be. It's going to hurt when I stand up. But I've now gone through the vast majority of the problems. The only thing that I've saved you are those last 2 cone problems on the back, because I feel like they're pretty straightforward. Without further ado, that completes the Related Rates extended assignment. Hopefully this has been informative and useful to you. If not, please don't tell me this particular one, because it took forever. Have a good day!